Well, good morning everyone, and welcome back to the Biotransport class at the University of Toledo. Today we'll do lecture number 4. We'll wrap up chapter 3, and remember that some of the key takeaway points from chapter 3 would be osmotic pressure and the Van Hoff equation, as well as Starling's equation, which allows us to calculate the filtration flow across a membrane due to the combined effects of the hydrodynamic pressure and the osmotic pressure. That's equation 3.4. And then we also looked at the hydraulic conductance, the LP term in that equation, and we developed a model that allows us to relate the different variables and combine them in a way that gives us an equation that we can use to predict hydraulic conductance for a given membrane and given solvent that you have filtering across that membrane. So yeah, we'll look at another example from chapter 3 on how to use Starling's equation. We'll just focus on what's going on with the capillary and the filtration flow from a capillary. And then we'll jump into chapter 4 and get started with fluid mechanics. So let's go to the lecture then. Now, as I mentioned in one of the earlier lectures, it's the capillaries in your body. That's where all the mass transfer action occurs. That's where oxygen gets transported, key nutrients and waste products and so on diffuse or get filtered across the capillary. So it's important to talk about capillaries for a few moments here, just so we have some background on this. And in table 3.3 summarizes some of the key capillary characteristics. We see that their diameter is on the order of about 10 microns, maybe 8 to 10 microns. Their length is only a millimeter, so they're not very long. And they also have a wall thickness of about a half a micron, and the average blood velocity in a capillary is about 0.05 centimeters per second. The actual pores in the capillary wall, the openings, those intercellular cliffs through which plasma can filter, the total surface area fraction, I mean, if you took the whole circumferential area of a capillary and then figured out the cross-sectional area of all the pores, it turns out that that pore fraction is only about 0.001. So the capillary wall is not a very porous material. Now the pore diameter, we talked about that earlier, is about 6 to 7 nanometers. So that means that solutes who have molecular weights higher than about 50,000 will not be able to cross the capillary wall, and that explains why the protein concentration in the plasma within the capillary is much higher than what we find in the surrounding interstitial fluid. Now the pressure coming into a capillary, a little drawing down here, if we just draw a capillary here, it's just a cylinder here. We've got blood coming in. This is the capillary. A just denotes the arterial end of the capillary, and V denotes the venous end of the capillary. The blood pressure coming into a capillary is only about 30 millimeters of mercury. Remember, the normal systolic pressure of blood is about 120 millimeters of mercury, and the diastolic pressure is about 80 millimeters of mercury. So what happens by the time you get down to the capillary level, these pulsations have dampened themselves out, and because of the resistance to fluid flow, the pressure is actually decreased at the entrance to the capillary to about 30 millimeters of mercury. Now the blood flows through the capillary, and because the pressure in the interstitial fluid is only about -3 millimeters of mercury. So it's interesting that the interstitial fluid pressure is actually subatmospheric, and these are also gauge pressures, so these aren't absolute pressures. If you wanted to get the absolute pressure, you'd have to add 760 millimeters of mercury to each of these these pressures that I'm giving you. So remember, gauge pressure is what you would measure with a like a tire gauge. Okay, when the tire, if you're measuring the pressure in your bicycle tire and the gauge reads 0, you got a flat tire. If you have a nice road bike, that that pressure might be as high as 110 to 120 psi. But it does work out through precise measurements that the interstitial hydrodynamic pressure is actually a negative 3 millimeters of mercury. Now, since the pressure then in the capillary is higher on the inside of the capillary than in the interstitial fluid, that causes a filtration flow. That's what this arrow shows here. At the arterial end, the flow is actually out, so we're actually losing and filtering plasma across the capillary wall. Now, we also have to take into account the pressure drop through the capillary, and that's what I call a P sub V over here. So by the time the blood gets to the end of the capillary, its pressure is dropped to about 10 millimeters of mercury. And if you average the inlet pressure and the outlet pressure, the average pressure turns out to be about 17.3 millimeters of mercury inside of the capillary. So that's the average pressure of the blood in a capillary. And you're probably wondering, well, why isn't it 20? Because 30 plus 10 divided by 2 is 20. Actually, the capillary kind of increases in cross-sectional area as you move down to the venous end. And because of the geometric averaging within a cylinder, it affects the averaging technique. So that's how they end up with the 17.3. So there's your mean pressure. The colloid osmotic pressure, which is called pi sub, plasma. Yeah, this is the colloid osmotic pressure of plasma, is 28 millimeters of mercury. One of the homework problems you're going to have from Chapter 3 talks about that pressure. But what the colloid osmotic pressure is, colloid just means that's the osmotic pressure due to the retained proteins in the plasma. Okay, so that's what we mean by the colloid osmotic pressure. Now, the interstitial fluid colloid osmotic pressure is only 8 millimeters of mercury. So once again, we can see the difference in these numbers represents the difference in the concentrations between the two regions. Now you can see that I have the arrow showing the filtration flow actually going back into the capillary at the venous end of the capillary, and you're probably wondering, well, how do I know that? And if there's a difference between these two flow rates, that would be the net loss due to filtration across the capillary. Well, we can use Starling's equation and do some simple calculations to figure out what the direction of the filtration flow is in a capillary. And these calculations that I'm doing is, even though we're talking about a capillary, remember this could be a hollow fiber tube within that hollow fiber device I showed in one of the earlier lectures. So, just because we're talking about a capillary, it's a good example, and it applies in a general sense to any type of membrane system. So, at the arterial end of the capillary, we can calculate then the flow rate of the fluid across the capillary wall using Starling's equation, equation 3.4. Now the way we would do this is we don't necessarily need to know what LPS is. All we want to know is what the sine of Q divided by LPS is. If that ratio is positive, is a positive number, then that tells us at that particular point in the capillary the flow would be out of the capillary. On the other hand, if that term became negative, then we would have flow back into the capillary. So when you do that calculation like I show in this paragraph, here's the incoming pressure. This is at the arterial end. Okay, so we're talking arterial end. So this is the hydrodynamic pressure of the blood. This is the minus 3 millimeters of mercury in the interstitial fluid. That's its hydrodynamic pressure. And then we have the osmotic effect. This would be the colloid osmotic pressure in the blood and the colloid osmotic pressure of the proteins in the interstitial fluid. And you can see that bracketed term comes out to be 13 millimeters of mercury. So that tells us then at the arterial end of a capillary, the filtration flow is such that fluid is actually leaving the capillary and going into the interstitial fluid space, which bathes the cells of your body. Okay, at the venous end, we can do the same calculation, but notice now that the venous pressure, hydrodynamic pressure, has dropped to 10. We still have the interstitial fluid hydrodynamic pressure of -3 millimeters of mercury. We still have the same osmotic pressure driving force, but notice how the bracketed term is now negative, a -7 millimeters of mercury. So that tells us that the flow is actually going to reverse. So what got filtered out at the beginning is now going to start being reabsorbed back into the capillary. Now, if we do the same calculation based on the mean value of the blood hydrodynamic pressure in the capillary, as shown by this little calculation here, you can see it's a very small number, 0.3 millimeters of mercury, but it's positive. So what that tells us is that in an average sense for a capillary, there's going to be a net loss of a fluid from the blood. And what happens then is that's why you have a lymphatic system in your body. The excess fluid that drains into the interstitial fluid space gets reabsorbed by the lymphatic capillaries, and that gets delivered back up into up around your chest area. There's veins where the lymphatic system dumps back into the cardiovascular system, and you recover that fluid that's been filtered out by the capillaries. So in a net sense, you're not losing fluid, it's just being cycled through your body, and everything works out fine. Now you're probably wondering, well, how much is this filtration? Is it significant? Is it a lot? Can we estimate what the value of that is? And that's what's illustrated in example 3.3. The problem says to calculate the normal rate of net filtration for the human body. Assume the capillaries have a total surface area of 500 square meters. That's about what it is for an adult human. And if you're trying to figure out and wrap your head around how much 500 square meters is, if you were at a football game, it'd be pretty much the same as the surface area from the 10-yard line to the goalpost. Okay, 10 yards times a 50-yard width for a football field would give you 500 square yards, and we're just, for argument's sake, saying a square yard and a square meter are about the same. It would be a little bit more of that, but at least you can visualize how much capillary surface area you have in your body, which is really tremendous. And now you can see why that's where all the mass transfer action happens in your body. Without that, you wouldn't be able to stay alive, because you wouldn't be able to have enough transport of the vital nutrients and oxygen that your body needs in order to live. Okay, so we got the surface area. We're going to assume that the tortuosity of the slit pores is equal to 2. So the openings in the capillary wall, the actual flow path is about twice the thickness of the capillary wall. That number comes from people studying with electron micrographs of the capillary. They've been able to see these slit pores and get an idea of their length. And that the slit pore surface area I mentioned earlier is 1/1000th of the total capillary surface area. So how would we make the calculation? Well, we would model this then as a porous structure of the capillary wall as a series of parallel rectangular slit pores with a thickness of 7 nanometers. So rather than taking them as round, we're going to go with the idea that they're rectangular slit pores, and we'll use the rectangular version of the equation that we developed in the previous lecture for the hydraulic conductance. The plasma filtrate may be considered to be a Newtonian fluid with a viscosity of 1.2 centipoise. Later in today's lecture, we'll start talking about what we mean about Newtonian fluids and what we mean by viscosity and so on. But for now, just remember that that number just represents the flow resistance of the plasma. And the mean net filtration pressure, or the effective pressure drop for the capillary, the mean value of that we just calculated when I was walking you through at the beginning of this lecture. So we just calculated that to be 0.3 millimeters of mercury. So we can use equation 310 to calculate the hydraulic conductance, and then we get the net filtration flow rate from equation 3.4 using the hydraulic conductance and the surface area. So this is kind of a busy calculation. You'd have to go back and look at equation 310. Once again, we write out the dimensional equation. We're working in strict SI units in this case. And you can see that in SI units of meters squared second per kilogram, the hydraulic conductance is quite small, 3.4 times 10 to the minus 12th. Okay, so we go to equation 3.4. We got the LP value. Here's the surface area, 500 square meters. There's the effective pressure drop, some units conversions. We crank it all out, and the net filtration rate across all the capillaries in your body, the net loss of fluid from the circulatory system is about 4 milliliters per minute. That would be about a quarter of a liter per hour. If you think about it, that's pretty significant. In 4 hours, that would be a liter of fluid has leaked across all your capillaries. And you can see if that fluid was not being reabsorbed and brought back to the circulatory system by the lymphatic system, you'd have some serious problems going on in your body. So that's all we're going to talk about in chapter 3. The rest of the stuff in chapter 3 you can ignore, because it kind of parallels some things you've probably already learned in physiology. Okay, so chapter 4 is the physical and flow properties of blood and other fluids. So we'll kind of use blood and plasma as our model biological fluids, and the things that we're actually developing here are general enough that it applies to all kinds of fluids. So there's no limitation. Once you learn fluid mechanics, you can apply it to whatever type of fluid you're dealing with. And one of the first things we'll look at would be the physical properties of blood. And there's some things in here I want to just tell you about before we jump into table 4.1, which summarizes all those physical properties. Recall that the chemical composition of the plasma was earlier shown in table 3.2. We saw in there that proteins represent then about 7 to 8 weight% of the plasma. The major proteins found in plasma are albumin, which has a molecular weight of 69,000. And remember, albumin can't cross the capillary wall, so it's retained and generates the colloid osmotic pressure. That's one of the major duties of albumin, is to regulate that osmotic pressure of your blood so that those filtration rates are proper within your body. People that have, microvascular disease and stuff get leaky capillaries. The albumin leaks out, and that leads to all kinds of problems. Edema or localized swelling would be one of the problems. People in advanced liver cancer, that your liver makes albumin, and if you're not making albumin anymore, then you get what's called ascites, and fluid starts to accumulate in the abdominal region because it's leaking. Basically, it's leaking out at a higher rate than it can be reabsorbed. Globulins are the immunoglobulins, and these are primary proteins that are used to fight diseases. So they're a couple grams per 100 milliliters. Remember, 100 milliliters, as shown here, is also a deciliter. It's kind of one of those crazy units that the medical field likes to use. So a lot of times they normalize things in terms of a deciliter. Fibrinogen is the major clotting protein. that when it becomes activated forms fibrin, which is the tangled web of a blood clot that catches the other cells and forms the clotty matrix that we see when we have a scab and so on. So that has a real high molecular weight of about 400,000. So those are some of the major players there. The cellular components of blood, just to review this for a few minutes here. There's a couple different cell types that we have to be aware of. The most abundant cells are the red blood cells or erythrocytes. I like to just call them RBCs. So if you hear me saying RBCs, it's the red blood cells. They're about 95% of the cellular component of blood. Their major role is the transport of oxygen through the use of hemoglobin that's contained within the red blood cell. And note that the density from table 4.1, that the density of a red blood cell is higher than that of plasma. So they will tend to settle out. If the blood's not moving, the red blood cells are going to sink down. And the red blood cell volume fraction is called the hematocrit of the blood, and typically varies between about 40 and 50%. The true hematocrit is about 96% of the measured hematocrit. So it's just a matter of how well you spin the sample down and how well those RBCs can pack themselves when you're making the measurement of the hematocrit. Okay, so let's see. We also have platelets, which are involved in clotting. They're about 4.9% of the blood cell volume, and the remaining 0.1% of the cellular component of blood consists of white blood cells, WBCs, or what are also called leukocytes, and they form the basis of the cellular component of the immune system. And since the WBCs and platelets only comprise about 5% of the blood cell volume, we can pretty much ignore their effect and just treat blood as just being a soupy mixture with red blood cells in it. That's the predominant cell type. So let's take a look then at table 4.1. This is just a reference table. Just be aware that it exists when you're working homework problems and so on. You can consult this if you need any data. And these are just nominal values. Whole blood just means you got everything in it, all the cellular components in the plasma. The pH is typically around 7.4. The viscosity of blood at 37 degrees C is on the order of 3 centipoise at high shear rates. We'll talk about shear rates in a little bit, but the easiest way to think about shear is to take a deck of cards, hold them in your hand, and if you spread them out slowly, you're shearing the deck of cards. Okay, so shear rate's the rate of deformation. If your hand moves real slow over the cards and you spread them out slowly, that's a low shear rate. If you do it really fast, that's a high shear rate or a high rate of deformation. So deformation is also the change in the velocity, the derivative of the velocity with respect to the direction normal to the deck of cards. Okay, so the shear rate's going to be the velocity in the direction that your hand's moving that's causing the shear. We would call that, say, Vx, and the y direction would be going into the deck of cards. So the shear rate's going to be dVx dy, which is also the rate of deformation. You might have talked about that when you took biomechanics. Here's the specific gravity. Here's some hematocrits. Males tend to have a higher hematocrit than females because of testosterone seems to have a significant effect of that. The whole blood volume is about 78 milliliters per kilogram, about 5 liters for the 70 kilogram standard human being. The plasma or serum, this is its colloid osmotic pressure in millimeters of water. pH. Viscosity of plasma is less than the viscosity of blood at high shear rates. Okay, It's just a little bit, the plasma viscosity is a little higher than water because of the presence of all the other junk that's in there. Erythrocytes, RBCs, their specific gravity is 1.098. Here's the number of red blood cells that you have per milliliter of whole blood. That 109 should be a 10 to the 9th. Production rate, average lifetime of a red blood cell is about 120 days. They get removed from the body, from the bloodstream by the spleen, and the hemoglobin gets broken down and converted by the liver into bilirubin, which gets excreted out in your bile. Here's the production rate of red blood cells, leukocyte counts and their size. Leukocytes, white blood cells, tend to be quite a bit bigger than the red blood cells. So that's just a summary then of what's found in blood. And the next thing we want to start talking about is what's called rheology. And rheology, analogy is the study of something, and rheo relates to the flow. So a rheostat controls the flow of electricity. Rheology is the study of flow, and what we mean by rheology is the study of the flow of fluids. And what it has to do with is it's concerned with the deformation and the flow behavior of fluids. There's some very basic fundamental physical phenomena that's observed with the flow of fluids and the behavior of fluids, and we're going to get to that by a simple thought experiment. We'll put some mathematics to a thought experiment, and we'll come up with some really useful concepts, which ultimately leads us into developing equations that describe fluid mechanics. And our understanding of the flow behavior then of fluids begins by exploring the relationship between shear stress and the shear rate. Now, I just talked about shear rate being the rate of deformation of the deck of cards, and the shear stress, remember, is a force acting parallel to a surface. So if you took the force that you applied to the deck of cards and divided that force by the cross-sectional area of the deck of cards, that would give you the shear stress. And then the shear rate is the rate at which the cards deform. So, if you were, taking movies of your deformation of a deck of cards, and you did this at different speeds of movement of your hand, you would start to see that there's a relationship between the applied shear stress, how much force you apply to the deck of cards, and the rate at which the deck of cards are deformed. And the same thing is actually happening within fluids, and we can come up with a thought experiment to investigate this. And then what we're interested in finding then is what is that relationship for a fluid between the shear stress and the shear rate. So the way we do this is shown on in figure 4.2. And we'll talk more about that, but before we talk about that, I need to kind of give you a little background on some things so that you can totally understand what I'm going to be talking about. And this stuff gets pretty deep, so you really got to think about this stuff in a deep sense. And what we're doing here is, let me show you the thought experiment, and then we'll explain some of the details. That's probably the best way to get into this. So that's shown up here at the top. So what we have is imagine we've got a large flat plate down here, very long and very wide coming out at you. And then we have another very long plate, very wide coming out at you plate. And between these two plates we confine a fluid, a very thin layer of fluid. And the two plates are separated by the distance h. Now at time equal to 0, the two plates are stationary. They're not moving. So if we went across the thickness of the fluid, we would find that the velocity everywhere in the fluid is 0. And then what we're going to do is at time equal to 0, we're going to keep the top plate stationary and apply a force F to the bottom plate and cause it to start to move to the right. And by doing that, we're going to induce motion into the fluid, and from that motion we're able to deduce the relationship between shear stress and shear rate. Now, as part of that, there's a couple things we need to talk about. We're going to develop this a little more later on. You'll see naturally through something called boundary layer theory where the Reynolds number comes from. But in transport phenomena in engineering, there's a lot of what we call dimensionless numbers which relate different physical phenomena one to the other. Okay? And one of the most important numbers in fluid mechanics is called the Reynolds number, which we abbreviate by R sub E. It's named after a guy named Reynolds who was a great fluid mechanics guy, and they honor him with this number. And the way we calculate the Reynolds number is you take the fluid density times the velocity, the average velocity or the reference velocity of the fluid. You would know that as the engineer. And we multiply it by a characteristic dimension, some dimension that defines in a characteristic way the size of the system being analyzed. And you divide that group by mu, recall, which is the viscosity. And what this is physically, it's actually the ratio within a fluid of the inertial forces acting on the fluid divided by the viscous forces acting on the fluid. And if the viscous forces are much, much higher than the inertial forces, then the Reynolds number is going to be less than 1, and we have what we call viscous flow. So viscous flow would be a very viscous fluid flowing through a very small diameter tube. I kind of talked about this the other day. I was talking about the pores in a membrane, and I was telling you when we were developing that hydraulic conductance equation that we would expect that flow to be very viscous because the characteristic length would be the diameter, and that diameter is very small, the velocity is very low, and the viscosity relative to those terms is high, so that gives us a low Reynolds number, and we have what we call laminar flow. And laminar flow is that nice glassy flow, and I gave you some ideas of what it means in terms of soldiers marching in their ranks and files. On the other hand, if the fluid is moving really, really fast, then the velocity is going to be really, really high, and you get a situation where the forces acting on the fluid are dominated by inertia. Inertia is the motion of the fluid. The high velocity of the fluid is much, much greater, those forces, than the viscous forces. So the Reynolds number is really high. Now when the Reynolds number gets way, way higher than 1, then what happens is all hell can break loose in the fluid, and we transition from laminar flow into turbulent flow. So there's always going to be a critical number for a system that you're analyzing at which the flow transitions from laminar flow to turbulent flow. And turbulent flow is very chaotic. There's large, lateral mixing of the fluid. There's eddies and swirls and all kinds of wild things going on. And everybody has seen turbulent flow. If you've been canoeing or anything and you see the water rapidly going over rocks and stuff like that, that induces a lot of turbulence. I mentioned your faucet in your sink in the kitchen. Just jack the water flow rate up really high, and you can see the flow transition from laminar to turbulent flow. Okay, so that's just laying out the physical situation, a little background. There's some more details in this paragraph that I want to mention right here. The velocity of the lower plate is sufficiently low then that the fluid motion is not turbulent. Okay, so in our thought experiment we're focusing strictly on laminar flow. The fluid motion's laminar. Okay, and I tell you about what laminar flow is, blah, blah, blah. Okay. Now, fluid velocity, you have to remember, is a vector. There's three components to a vector, and since this system here would be analyzed in Cartesian coordinates, our velocity vector, which we'll call v with a little squiggle on top, would be Vx, Vy, and Vz. Those would be the three components of the velocity that we would expect within the flow region in a general sense. However, when we look at figure 4.2, Vy and Vz are both 0. Now Vx is going to be the velocity in the direction of the flow, the direction that the plate is moving. Vy is going to be normal to the plates, and Z is going to be normal to the paper. Z is the direction coming out at you. Now, if you think about it, you can think physically about this problem. And part of what transport does too, I just want you to realize this, is transport is building up your engineering intuition. A lot of times we may not be calculating numbers, but you're just in situations where you have to think about, what in the world is going on in this system, and transport gives you a logical basis to understand how things are working. The last thing you want to have as an engineer are just opinions. Opinions are worthless. They're thoughtless. Engineers, we only deal in facts and intuitions that are grounded in engineering science. Okay, so that's one of the things that transport's doing. It's going to be training your brain to think about real world problems and design and so on in a logical sense, and not just shooting from the hip type of a thing where you're just shooting off an opinion and your opinions don't mean anything. Okay, so we would expect then Vz to be 0 if the plates are very, very wide and the flow is in the x direction. For our thought experiment, there wouldn't be any flow in the z direction. Okay, the separation between the plates is very, very small, and in the limit there wouldn't be any flow in the z direction for sake of argument. Also, Vy is going to be equal to 0 since there's no motion of the lower or upper plate in the y direction, and there are no holes in either sides of the plates. So when that bottom plate starts to move, there's nothing going on that would cause the fluid to flow in the y direction. That could only happen if the plates were oscillating, or if along the length of the plate there were holes and fluid was flowing and leaking out into the y direction. So right away we can eliminate two of our velocity components, and we know that our velocity only depends on Vx. Okay, let's see what else. Okay, so in that situation then, if you're looking at figure 4.2, the only velocity component is that in the x direction, Vx. And now, this is where we also have to understand that Vx, though, can depend on the three coordinates and time. Okay, this is an unsteady problem when it starts up, right? It's at the fluid's at rest, the plate starts to move. So there's an unsteady startup period, and then the velocity, we could think about it, it may depend on x, y, and z in a general sense. Now, since the lower plate is set into motion at t equal to 0 and the fluid initially is not moving, there will be a transient time period during which successive layers of the fluid will begin to move. So this is what's interesting, and this is what's shown in figure 4.2 here, is you can see that our velocity profile, right after the plate starts to move, the only fluid that's going to be moving is the fluid adjacent to the plate. Now, one of the fundamental rules of fluid mechanics is the no-slip boundary condition. A fluid attaches itself to the boundary and goes at the velocity of the boundary. So the velocity of the fluid at the surface is going to be the same as the boundary. The velocity of the fluid up here, which is tagged to the upper plate, will always be 0 because the upper plate's not moving. And that's called the no-slip boundary condition. Now as time goes on, what's going to be happening here is we're going to have the transport of x momentum, the movement of this plate in the x direction. Momentum is going to be transported from the x direction to the y direction. And it's the transport or diffusion of that momentum into the fluid which causes successive layers of fluid to start to move. So as you can see in this diagram right here, if we were measuring the velocity profile in the fluid at some later time, we would start to see that there would be some distance at which the velocity would go to zero, and then beyond that, this fluid out here hasn't even noticed the fact that the lowest plate, that the lower plate's moving. However, if we run this system sufficiently long and we get to steady state, then all the fluid elements in the fluid are moving, with the exception of those at the surface of the top plate. Because of the no-slip condition, their velocity is going to be equal to zero. And at steady state, the velocity profile, it turns out that it's just going to be linear. It's going to be a straight line, just as I have it shown there. And this has been observed in numerous experiments and so on. So that this kind of phenomena, it's easy to see these things visually with dyes and things. People back in the early days of fluid mechanics did all kinds of clever experiments to show this. But even our intuition just tells us as well that that's the case. But like I said earlier, what's important here is the transport of momentum, the diffusion in laminar flow of x momentum in the y direction. Okay, and that's what I'm talking about here in this paragraph. Momentum flows or diffuses from a region of high velocity to a region of low velocity. So that's kind of an interesting concept, because if you think about the analogy to mass transfer is the diffusion of a substance from high concentration to low concentration. So the driving force for mass transfer is a concentration difference. The driving force for heat transfer is a temperature difference. The driving force for momentum transfer in a fluid is a velocity difference. And what's really cool about transport phenomena is that in a general sense, all of these transport mechanisms are described by similar equations. So if you sort of learn fluid mechanics, by default you'll really understand mass transfer and heat transfer. It's all wrapped up into the same kind of a concept. So it's kind of neat that these are all unified together. Okay, now you're probably wondering, where in the hell is he going? Well, I thought we were trying to figure out the relationship between shear stress and shear rate, and he's just been rambling on about this little thought experiment. Okay, well, now that we know what's going on and we get to steady state, now we can start talking about shear stress and shear rate and start to develop some equations around this. So after a sufficient length of time, a steady state profile is obtained, and the velocity profile, Vx, only depends on y. Now you're probably saying, well, why doesn't it depend on x or z? Well, it doesn't depend on z because z is coming out at you, and because the plates are very, very wide and the thickness h is constant along that distance, this profile should exist all the way out, perpendicular to the page. So there's no way that this velocity profile is going to depend on z. Similarly, since the plates are very, very long relative to the thickness of the plates, when we get to steady state, this profile is going to look the same at any position x, along the length of our experiment. So that velocity profile is not going to depend on x. The only variable it can depend on is y, and through some simple algebra then we can write that Vx of y, the x velocity, how it depends on y, is simply given by this equation here. The average velocity v divided by h times h minus y. Okay, you can just get that by inspection. And then it's always good to check an equation like that to make sure that the equation makes sense. So if you set y equal to 0, the h's cancel out, and at y equal to 0, you're at the bottom plate, and the velocity is v. When you're at the distance where y is equal to h, you're at the top plate, which is stationary. H minus h is 0, and the velocity is 0. So we see that this equation represents what's happening to the fluid velocity. Okay, now at steady state, in order to maintain steady state, you're going to have to continue to apply a constant force to overcome the resistance of the fluid and maintain the motion of that lower plate. So for the situation shown in figure 2, the shear stress on the lower plate is simply going to be F, the steady state applied force, divided by the cross-sectional area of the lower plate. So, imagine you could do these experiments at home. If you got some really large plates and you put some fluid between the plates, and you had a way of measuring the force as you move the lower plates, you would get force, right? And the smart way then to analyze your data, you take that raw data of force and divide it by the surface area of your plate, because in an engineering stress sense, that's, shear stress is a cool variable, and it becomes independent of the size of the system. Okay, so you normalize the force by the surface area to take the size of the system out. And that's how we get the shear stress. So F over A is the shear stress. Now what about the rate of deformation? Well, it turns out that the shear rate at any position in the fluid is defined, as I mentioned earlier, would be dvx dy, the negative of dvx dy. You can get to that from mechanics of materials. You probably studied this. We got to it in a simple sentence, thinking of the sliding of a deck of cards. It just sort of comes to your brain that the rate of deformation is dvx dy. And once you have your velocity profile here, if you take your dvx dy, take the derivative of that guy, you find out that the shear rate is just v over h. So in a physical sense, the shear rate acting on this fluid or acting on a deck of cards would just be the velocity of the surface divided by the thickness of that layer. That would be your shear rate. If it was a deck of cards, it'd be the velocity of your hand moving across the cards divided by the thickness of the card. That's your steady state shear rate. Now shear rate has the units of reciprocal time. Okay, so it's important to remember what the units of that. Typically shear rate has units of per second. And shear stress would have units of like pascals, okay, newtons per square meter. Now what's interesting, if you did this experiment at home, you measured the velocities, you know the thickness of the plate, you got your shear rate, and then you measured the force that you had to apply to get that velocity and all that, and you did the shear stress calculation, then you'd say, okay, I want to take all this data that I've obtained at different plate velocities and plot it on a graph. I want to plot shear stress versus shear rate. What does my data look like when I plot it? And that leads us to what's called Newton's law of viscosity. If you are doing your experiment on a fluid like water, you would find that there's a linear relationship between the shear stress and the shear rate. Okay, and that's called Newton's law of viscosity. States that for laminar flow, the shear stress is proportional to the shear rate. So when you plot your data of shear stress versus shear rate, that data is going to fall along a straight line. And the slope of that line is going to change for different types of fluids. And the reason that the slope changes is because the slope is the physical parameter that we call viscosity. So that's how we get viscosity. And this little thought experiment that we went through, gave us a logical way of coming up mathematically with what we mean by viscosity. And viscosity represents then the flow resistance of the fluid. So a fluid that has much higher viscosity is going to have a higher slope. It's going to take more force to deform that particular fluid. And viscosity is usually expressed in the following units, where 1 poise, okay, a poise is the old standard unit, 1p is equal to 100 centipoise. And it's a poise is also 1 gram per centimeter per second, which is also equal to 1 dynesecond per square centimeters, and so on. You can see all these units. The key one to remember is that 1 centipoise is 0.001 Pascal seconds. Pascal seconds is the SI unit that's used for viscosity. So we can say then for the situation in figure 4.2 that Newton's law of viscosity can be stated as what I have right here, that the shear stress is equal to the viscosity times the shear rate. And most simple homogeneous liquids and gases, benzene, alcohol, air, all of these guys follow Newton's law of viscosity, and we call those fluids Newtonian fluids. So this is probably a good place to stop. Why don't we just quit right here, and we'll pick up and continue to talk about shear stress and shear rate and the relationships between those guys, and which leads to Newton's law of viscosity. But then we also have to ask ourselves, well, what about these weird fluids that don't behave in that linear way? And for those fluids, we call those guys non-Newtonian fluids, and we come up with different expressions for the shear stress shear rate relationship for non-Newtonian fluids. So I'll see you back here on Friday.